again. Welcome back for day 3. So hopefully your knowledge check went well yesterday. I've got my trusty whiteboard here. Man, mirrors are hard. Okay, so here's our equation on top that you can see with the delta H, so giving us our whole thermochemical equation. I don't know why this is so hard for me. There we go. Your first step is to convert those 5 grams of methane into moles by dividing by molar mass to get 0.311 moles of methane. And then because our delta H is for 1 mole of methane, as you can tell in the balanced chemical equation, all we have to do is take the moles that we have, so 0.311, times the delta H per mole, so that 890 something, to get negative 276 joules. Any questions, please let me know, and I would be happy to help. All right, so now we're going to start talking about enthalpies of formation. This tends to get a little bit more complicated for a lot of people because the equations can be very long and normally take up my whole classroom whiteboard. Our next knowledge check, I have about half a page of work just to kind of work it out. So just stick with me. I know it's going to be a little bit harder. But an enthalpy of formation, which is this delta H and then a little degree sign and then an F, is equal to the enthalpy change when 1 mole of a compound is formed at standard temperature and pressure. Most enthalpies of formation are negative, and they're... What, buddy? Can you wait? Okay. Most enthalpies of formation are negative, and they are normally exothermic because decomposition is... I don't know what I'm saying. Okay. Normally exothermic reactions are... Hi, buddy. You got me all distracted. Yes, thank you.
Can you open it? Yeah, except the foreheaded eyeball.
Go play. Gooper. All right, we're going to try that again. Most enthalpies of formation are negative. These are normally exothermic reactions. Decomposition generally is a normally endothermic reaction, so it will absorb heat. And elements in their standard states have an enthalpy of formation of 0. So that's really, really important because if their enthalpies of formations are 0, then you do not have to include them in our equations. So remember, standard states would be like O2 because it's a diatomic molecule as a gas, because that's what we normally have oxygen present as. Or carbon as a solid, because carbon is always solid at room temperature. Calculating those enthalpies of formation, so when we're looking at a standard enthalpy change for a given thermochemical equation, it's going to be equal to the sum of the standard enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants. So again, ignore things in their standard states. This right here is our big long equation. These symbols right there are called sigmas, and they represent the sum of. So you take the sum of the enthalpies of formations of the products minus the sum of the enthalpies of formation of the reactants to get that enthalpy change for the reaction itself. So in this example here, we're going to have aluminum as a solid reacting with an aqueous copper. So this would be like a copper sulfate, something in solution where the sulfate is our spectator ion and not involved in the reaction. It's going to yield an aqueous aluminum and a solid copper. Your coefficients are going to end up being what we multiply by. So because aluminum here is a solid, and it almost always is a solid at room temperature, we're going to ignore this one. Because copper is a solid here, you ignore that one. And we get the enthalpies of formation of our liquid aluminum multiplied by its coefficient minus the enthalpy of formation of our liquid copper multiplied by its coefficient. So in this knowledge check, it's going to be, like I said, a little bit longer. Hold on a moment. Yes, dearest. I would love to.
Mommy, I have steam power in my head, so I see Eli and Daddy and you in my head.
Oh, that's excellent. Okay, so we're going to talk about this knowledge check now. Benzene, which is C6H6, is used in the manufacture of plastics and is often a carcinogen. It affects the bone marrow. Long-term exposure to benzene has been shown to cause leukemia and other blood disorders. The combustion of benzene, because it is highly combustible, is given as follows. C6H6 liquid plus 15 halves O2 as a gas will yield 6 CO2 gas plus 3 H2O liquid. The delta H for this whole reaction is negative 3,267.4 kilojoules. Our heats of formation of carbon dioxide are negative 393.5 kilojoules, and the heat of formation for water is negative 285.8 kilojoules. So you've got two questions to answer. What is the heat of formation of benzene, which is the C6H6? And what is the delta H for this reaction? Notice that it's the reverse reaction, and our coefficients are no longer as fractions.